This is section 3.1 on what's called derivative of a function. The definition, the derivative of a function with respect to x is the function f prime whose value at x is. So really all this is terminology. Derivative equals instantaneous velocity. It's the same thing. It means the same thing, except we have some notation and some vocabulary to introduce here. So here's the notation. F prime of x means this thing called derivative. And it's equal to the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. If a function has a derivative of x, we say the function is differentiable at x. Now, before we did instantaneous velocity, and we said, all right, this we're going to graph this function that represents distance, and when we do the secant line, that equaled average velocity. And then we talked about instantaneous velocity at a value at some x value, and we said, all right, well, let's drag this point and let's keep using secant lines to get closer and closer to the instantaneous velocity. Well, this is the same thing as finding the slope of the tangent line at this point, and when we find the slope of the tangent line, we are finding derivative, and we are finding instantaneous velocity. So if you hear instantaneous velocity, derivative, or slope of the tangent line, those all mean the exact same thing. It's this process. It's the limit as h approaches 0 of f of x plus h minus f of x over h. And then we'll have to do some algebra to reduce this to finally take the limit. Now, you need to memorize this. You need to memorize this formula for derivative, for instantaneous velocity, for slope of the tangent line. It all means the exact same thing. Now we have a bunch of notation that goes along with derivative. So this is notation, and it all means derivative. But it all depends on the context in which it's used. In the example I give, this word is either read or read depending on the context, depending on how it's used in the sentence. So we want to denote derivative in a number of different ways, and it'll all depend on how the question is asked. First of all, we have f prime of x. It said f prime of x, and it means the derivative of f at a value x. So you could see find the derivative at, let's say, a value of 2. Y prime, that's y prime, that means the derivative. Sometimes we have function notation, sometimes we have regular notation, and the derivative will be denoted depending on how we're using it. This is change in y over change in x, which is like rise over run. It's slope. Well, in the terms of derivative, it's usually written dy over dx. It's the derivative of y, derivative of the function y, with respect to the variable x. So x will be in the equation, for example, y equals 3x squared minus 4. If you're asked to find dy dx, that means we're going to find the derivative of y, and the variable that's being used in the function is x. df over dx, derivative of f with respect to x, another way to write that. And finally, d over dx, which just really stands for derivative of something with respect to x. So they all mean slightly different things, but they all mean derivative. Alternate definition of derivative, and this is at a point. At a point A, you can find the derivative by taking the limit as x approaches A. Notice it's not h approaches 0 down here anymore. It's x as approaches A of f of x minus f of A over x minus A. Now we're going to find the derivative of f of x here at the point 2, and we're just going to follow the formula. F prime of 2, f prime of A is 2 in this case, is equal to the limit as x approaches 2 of f of x. F of x is x squared minus 1 and minus f of a. So f of a is 2 squared minus 1. We plug the value in. And that's going to be all over x minus 2. And now we can simplify a little bit. Limit as x approaches 2. Well, let me say this. You can't plug 2 in this. We can't use substitution because we would have 2 minus 2, which is 0 in the denominator. So we're going to have to use a little bit of algebra to eliminate this x minus 2. All right, let's continue. We have x squared. Oh, let's see. Minus 1 minus 4 minus 1 is 3. All over x minus 2. Now that's equal to the limit as x approaches 2 of x squared minus 4 all over x minus 2. And now on top we have the difference of two squares. So we have the limit as x approaches 2 of x minus 2 times x plus 2 all over x minus 2. And now we can cross out the issue we had with the denominator being 0, and we have the limit as x approaches 2 of x plus 2, and now we can finally use substitution to solve this. We have 2 plus 2, and finally we have 4 as the limit. Now this is using what's called the alternate definition of derivative, and back here on slide 1, actually back here, this is the formal definition of derivative, formal. We have a formal definition and an alternate definition of derivative. Let's look at an example using the formal definition of derivative to find f prime of x given this function here. So we're going to go back to the very first slide, and we're going to use the formal definition to find this derivative. So we have the limit as h approaches 0 of f of x plus h. So we have 1/3 times x plus h to the third minus 2 times x plus h squared plus 6. There's your f of x plus h, and then minus f of x, which is 1/3 x to the third minus 2x squared plus 6. And that's going to be all over h. Well, we have to do a lot of algebra now. So we have limit as h approaches. Actually, I'm not going to write that because I'm going to write out the algebra first, and then I'll put it back into the limit. I want to just do this piece right there, which is x plus h times x plus h times x plus h. So we have x squared plus 2xh plus h squared. That's those two binomials multiplied together. And then we need to multiply that times x plus h. So we're going to distribute the x through the trinomial. We'll get x to the third plus 2x squared h plus x h squared. Then we'll distribute the h, this h right here, through this trinomial. So we'll have x squared h plus 2xh squared, and then plus h to the third. So finally, this is going to be x to the third plus 3x squared h plus 3xh squared plus h to the third. There's that binomial cubed. Well, we have the limit as h approaches 0 of 1/3 times this binomial cubed, which end up being this line right here, which is x to the third plus 3x squared h plus 3x h squared plus h to the third. Now we'll keep going on down the line. So we have minus 2 times x squared plus 2xh plus h squared plus, well, we have 6 minus 6. That's going to be gone. That'll cancel. And then we have minus 1/3. So I'll erase this plus. We have minus 1/3 x to the third, and then plus 2x squared. And that, once again, is all over h. We're trying to get rid of the h in the denominator. Let's see if that happens. Next, we have the limit as h approaches 0 of 1/3 x to the third plus x squared h plus xh squared plus 1/3 h to the third minus 2x squared minus 4xh, and then minus 2h squared. And on the end we have minus 1/3 x to the third and plus 2x squared. And once again, that is all over h. We have not gotten rid of the h yet. Let's see what cancels on the top. We have 1/3 x to the third minus 1/3 x to the third. Somewhere we should have, here it is, minus 2x squared plus 2x squared. Those are going to cancel out, and we can write what remains. So we have the limit as h approaches 0 of x squared h plus xh squared plus 1/3 h to the third minus 4xh minus 2h squared, and that's it. And it's all over h. Now, we've accomplished what we've set out to accomplish. Everything has an h, so I could factor an h out of the top, and that would cancel with the bottom h. So let's do that. We have the limit as h approaches 0 of x squared plus xh plus 1/3 h squared minus 4x and then minus 2. Now everything that has an h is going to go away because now we can finally plug 0 in, and what we end up with is x squared. That'll go to 0 when we plug 0 in. That'll go to 0. That'll go to 0. So we have x squared minus 4x as the derivative of the function. In the next slide, we are asked to find, this means the second derivative of x from the previous example. Well, fortunately, we can just take the first derivative and take the derivative of that, which will be the second derivative. So we have x squared minus 4x. So the first derivative is x squared minus 4x, and now we're going to use the formal definition to find the second derivative. Limit as h approaches 0 of f of x plus h, which is x plus h squared, minus 4 times x plus h. There's f of x plus h, then minus f of x, which is x squared minus 4x. And that's going to all be over h. Now we do a little algebra to simplify. We have the limit as h approaches 0 of x squared plus 2xh plus h squared minus 4x minus 4h, and then minus x squared plus 4x. And that is all over h. Well, we'll have some things that can cancel. The x squareds will cancel, and the 4x's will cancel, and what we should have left is everything with an h in it. So we have limit as h equals 0 of 2xh plus h squared minus 4h all over h. That's equal to the limit as h approaches 0 of 2x plus h minus 4 all over, well, not over h anymore because we canceled out an h from everybody. So that's what we end up with. Now we can finally plug 0 in to h, and we get 2x minus 4. Now we're going to have to do this 2 more times, but you can see that the function is getting smaller and smaller. To find the third derivative, we use the second derivative. So second derivative of x ends up being 2x minus 4. So now we have the limit as h approaches 0 of 2 times x plus h minus 4. There's f of x plus h minus f of x, which is 2x minus 4, and that's all over h. So we have the limit as h approaches 0 of 2x plus 2h minus 4 minus 2x minus 4. Actually, not minus 4, but plus 4. And that's all over h. So we have the limit as h approaches 0 of, let's see, the 2x's cancel, and actually the 4's cancel, and then what's left is these h's cancel, and we're just left with 2. So the derivative, the third derivative, is 2. Now we're asked to find the fourth derivative. So we start out with third derivative. Third derivative is simply 2. So now we got to find f of x plus h. So we have the limit as h approaches 0 of f of x plus h, which is just 2. There's nothing to plug x plus h into. Minus 2, there's f of x, all over h, which is the limit as h approaches 0 of 0. 0 over h is 0, so the fourth derivative is finally 0. In the last slide here, we have graphed this function right here, and we have graphed what we found to be its derivative on the same set of axes. The thin line is the x to the third, and the thicker line is the x squared. Notice that it was knocked down by 1. Interesting. Well, let's look at how these two functions relate to each other. Look, the slope of the tangent line, which is derivative, right here is 0. And the slope of the tangent line right here is 0. Now that's the original function, but look at its derivative's value. The value of the derivative is sitting right here at 0 and lined up perfectly with the value of 0. Now we have 3 different areas that we're going to look at in between the zeros, right here and right here. Notice what happens to the function. The derivatives, or the slope of the tangent lines, become increasingly more and more positive. And that's exactly what's happening to the graph of the derivative. As we go to the left, the values are becoming more and more positive, right along with the slope of the tangent lines getting more positive. Let's look at in between the two. Here's the original line right here, and the slopes are now going to get more and more negative until they hit this point right here. More and more negative, and then less and less negative, but yet still negative until we get back to 0 again. Now in the third section over to the right, the function right here is getting, the slope of the tangent lines are getting more and more positive as we go along, and look at the value of the derivative gets more and more positive.